I welcome you all in this lecture on S Plane T Junctions. Well, in the previous lecture on waveguide junctions, we have seen that a microwave junction is used for splitting or combining microwave power. In this lecture, we'll discuss S Plane T Junction, one such junction which is used for combining or splitting microwave power. Figure here shows a physical structure of an S Plane T. It is a three-port structure, 1, 2, and 3. There are 3 ports in an S Plane T. So the first thing is we'll see how is it formed. We have, say for example, a main waveguide. This is our main waveguide. So what we do is that, let me draw a waveguide first, a rectangular waveguide. This is how I draw it. This is a rectangular waveguide. Now, if I cut a slot along the width of this main waveguide, and then I attach another waveguide section, say for example like this. On cutting this rectangular slot here along the width, I attach another waveguide like this. So this is an S plane. This is an S plane T junction. So I am cutting a slot along the width of the main waveguide and attaching another waveguide. This is also called as this attachment. This arm is called as side arm or an H arm. So this is port number 1 of the main waveguide, this is port number 2, and this is port number 3, which is in the side arm. So this is a 3-port junction basically. Ports 1 and 2, as we can see, they are collinear. Ports 1 and 2 are collinear. They are collinear as they are in the same line. And port 3 is in the side arm, as I said. These ports 1, 2 and 3 are shown here in the main structure or in the physical structure of the waveguide as port 1, 2 and 3. Ports 1 and 2 are collinear, as I said, and port 3 is in the side arm. Now if I can draw, this is the axis of the main waveguide section, axis, and this would be the axis of, this is the axis of the side arm. This is the axis of side arm. Now if I connect a source, for example at port 1, the direction of electric field would be upwards. This is the direction of electric field. This would be the direction of electric field here, and this would be the direction of electric field at port 3. Now the magnetic field, so far is concerned, the magnetic field would be perpendicular to electric field, The magnetic field would be like this. This would be the direction of magnetic field. This is the direction of magnetic field, perpendicular to the direction of electric field. Electric field, as I said, would be like this. Electric field is like this, and magnetic field is shown by the black arrow. Likewise here, the direction of electric field is shown by this red arrow, and the magnetic field direction would be this. The electric field is perpendicular to magnetic field. Now if we can see, the direction of magnetic field is along the axis of the side arm or the H arm. That is why it is called as H plane T. H plane T junction. I repeat, the direction of H field is the same as that of the axis of the side arm. That's why it is called as H plane T junction. Now also all the ports so far are concerned. Port 1, if we can see, all these arms, this arm, and this arm, these all lie in the plane of magnetic field. This H plane T is also called as shunt T or current junction. Now the properties of this H plane T, the properties can be completely understood by its S matrix or scattering matrix. So let's try to find the scattering matrix of this 3-port network, this H plane T junction. Scattering matrix of H plane T junction. Since an H plane T junction is a 3-port junction, so its S matrix would be a 3x3 matrix. It will be a 3x3 matrix. So it would look like S matrix would be having these as elements: S11, S12, S13, S21, S22, S23, S31, S32, S33. These are 3x3 matrices. Since there are 3 possible inputs and 3 possible outputs to this 3-port network, so naturally the S matrix would be a square matrix of order 3x3. So in general, any element of this matrix Sij would be, like, as I said, is a 3x3 matrix. So that would mean that I can vary from 1 to 3, and J again can vary from 1 to 3, sorry. Both of these variables, they vary from 1 to 3. Let me draw it here. 1 to 3. Now if we look at the structure of this H plane T junction, if I draw a plane, for example, somewhere here, if I draw a plane here which bisects this T, so with respect to this plane, the structure is symmetric. So there's a plane of symmetry. So this is where the plane of symmetry lies, along this red line. This is the plane of symmetry. So if I draw a plane through this red line perpendicular to the plane of this T, so it will bisect it into 2 parts, which will be symmetric. We can also see from the physical structure, if I draw a line here, rather a plane here, which bisects it like this. So with respect to this plane, this structure is symmetric. So this is the plane of symmetry. plane of symmetry. So because of this plane of symmetry, the S parameters S13 and S23 must be equal. See, S13 must be same as S23 must be same as S13. So this is because of plane of symmetry. So the first thing that we have seen is that because of plane of symmetry, S13 is same as S23. Again, we know from symmetry property that Sij is same as Sji in general. Ijth element is same as Jith element, or S is same as S transpose. So S12 is same as S21, S23 is same as S32. But we have seen S13 is same as S23. Here we have seen S23 is same as S32. That means it has to be equal to S13. And further, S13 is same as S31. Further, port 3, the port in the side arm, is matched to the junction. So that means S33 is equal to 0. Now what I'm saying is that if we look at this structure, port 3 is matched would mean if I connect a signal source here, A3 would be the incident wave and B3 would be the reflected wave. S33, as we know, is B3 upon A3. So B3, the reflected wave from the port, would be 0, as this is perfectly matched to the junction. So that means S33 is 0 upon A3, which is 0. So that's what we have seen. That's what I have written here. S33 is 0. That means basically B3 by A3 is S33, but since port is matched, B3 is 0. There are no reflections, therefore S33 is 0. Therefore I can rewrite the S matrix as S matrix would be S11, S12, S13. Instead of writing S21, I can write S12. Instead of S22 would be the same as S22, and S23 here, S23 is same as S13, so I'll write S13 again. And again S31 is same as S31 as we have seen above, and S23 is same as S13. So this is what the matrix looks like. So there are only, if we can count 1, 2, 3 and 4, there are only 4 unknowns. So we need 4 equations to get these 4 S parameters. Now we know from unitary property of a lossless network, we know S into S transpose, S into S conjugate is a unit matrix. So that would mean S11, S12, S13, S12, S22, S13, 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 0. This is our S matrix, and its complex conjugate would be, S conjugate is S11, S12. Why this star, S13 star? This star represents the complex conjugate. S12 star, S22 star, S13 star, S13 star, S13 star 0 is equal to a unit matrix of the same order as that of S. So it would be 1 0 0 0 1 0 0 0 1. So unit matrix, as you know, all the non-diagonal elements will be 0 and the diagonal elements would be 1. Now our aim basically is to get the values of these S parameters. So we have these equations in the matrix form. We have the product of two matrices on the left side and a unit matrix on the right side. Now if I multiply these rows and columns, say for example, if I multiply row 1 by column 1, for example, if I multiply row 1 with this column 1, I'll get the first element 1. So if I multiply row 1 with column 1, we get S11 S11 conjugate plus S12 S12 conjugate plus S13 S13 conjugate is equal to 1. So we know if we multiply a complex number by its conjugate, we get the modulus square plus S12 square plus S13 square is equal to 1. Similarly, if I multiply row 2 by column 2, so that would mean I am multiplying row 2, this row 2, by this column. So when I multiply it, row 2 by column 2, I get this diagonal element. So row 2 by column 2 would mean S12 S12 star, so it would be S12 square plus S22 S22 conjugate would be S22 square plus S13 conjugate would be S13 square mod S13 square is 1. Likewise, I can multiply row 3 by column 3. If I multiply, say for example, if I multiply row 3, this row 3 with column 3, I'll get this element. So on multiplying row 3 with column 3, we get S13 into S13 star would be S13 square modulus square plus S13 modulus square plus 0 is equal to 1. So we have these equations. We have equation 1 here. We have equation 2 here. We have equation 3 here. So this means twice S13 square is equal to 1, which means S13 square is equal to 1 by 2, or S13 is equal to 1 upon root 2. So as I said, we have 4 unknowns, we need 4 equations. We have multiplied R1 C1, R2 C2, R3 C3. Now if I, for example, multiply R3 with column 1, so that would mean if I multiply, say for example, I multiply this row 3 with column 1. So in this case, I'll get a non-diagonal element. I'll get in this case a 0. So multiplying row 3 with column 1, row 3 with column 1. So I'm multiplying row 3 is this S13, S11. I'll use a different pen. I'll use black color. So if I multiply S13 with S11 star, row 3 column 1, S13 S11 star, S11 star plus S13 S12 star plus 0 into S13 star, so that would be 0. This would be equal to a non-diagonal element. This would be 0. So if we can look at this equation, S13 will be common to both these two terms, is equal to 0. But we have seen above S13 is equal to 1 by root 2. So S13 cannot be equal to 0 as it is 1 by root 2. So that means S11 star plus S12 star is equal to 0. Or S11 star conjugate basically is S12 conjugate, which implies S11 is minus times S12. Or this means S12 is minus S11. Now from above we have seen that if we look at equations 1 and 2, the right hand sides of both these equations are 1. So if the right hand sides are 1, so the left hand sides of these equations must be equal. So if I can write these left hand sides of equations 1 and 2, I'll see S11 square plus S12 square plus S13 square must be equal to S12 square plus S22 square plus S13 square. So that means S11 square S12 square plus S13 square, the left hand sides of these equations, is equal to S12 square S22 S13. S12 square S12 square plus S22 square plus S13 square. S13 square. See, S13 square and S13 square is on the both sides. Likewise, S12 square is on both sides. So this means that S11 square is equal to S22 square, or we can write S11 is same as S22. Now let me rewrite equation 1. So equation 1 is S11 square plus S12 square plus S13 square is equal to 1. S11 square plus S12 square plus S13 square is equal to 1. So we have seen S11 is same as S22. We have also seen S13. We have already calculated that S13 is 1 by root 2. S13 is 1 by root 2. This is where we have calculated S13 as 1 by root 2. So instead of S13 I can write 1 by root 2 square. Right hand we have a 1, and S11 and S12 so far are concerned. You see, S11 is same as S12. S12 is minus times S11. If I square it, that would mean S11 square is same as S12 square. So I'll write S11 square instead of S12. Instead of S12 I can write, instead of S12 I can again write S11. Minus and minus will become plus S11 square. This is from this equation. S12 is same as minus S11. So I am writing, instead of S12 I am writing S11 and then square, because square will take care of the negative sign. So this becomes 2 times S11 square plus 1 by 2 is equal to 1. So 2 times S11 square is equal to 1 minus 1 by 2, which is 1 by 2. So S11 square is 1 upon 4 and implies S11 is 1 upon 2. So if S11 is 1 upon 2, That means S22 is also 1 upon 2, implies S22 is also 1 upon 2. From this equation, S11 is same as S22. And also we have seen from above that S12 is minus times S11. So that means S12 from above is minus times S11. That means S12 is minus times 1 upon 2. As already said that there are only 4 unknowns that we need to know. So S11, S22, S12 and S13. So we know all these S parameters. So we can write the scattering matrices then. Let's look at the scattering matrices. So these are the 4 unknowns: S11, S12, S13, S22. These are the only 4 S parameters that we need to know. So let me write the S matrices then. So our S matrix basically is S11, S12, S13, S12, S22, S13, S13, S13 and 0. So this can be written as, now that we have found all these values. So S11, which is 1 by 2, S12 is minus 1 by 2, S13 as we have seen is 1 by root 2, S12 is minus 1 by 2, S22 is 1 by 2, S13 is 1 upon root 2, S13 is 1 upon root 2, S13 is 1 upon root 2, and this is our, so this finally is our S matrix. So as we have seen that an H plane T is basically a 3-port junction. Let me try it. So this is a cross-sectional view of an H plane T junction, which has 3 ports. Port 1 and port 2, they are collinear, and port 3 is the port. So for a 3-port network, if this is port 1, let us assume this is A1, this is A2, and this is A3. This is A1, this is A2, this is A3, the incident waves at these ports. And say for example, this is the reflected B1, this is the reflected wave B2, this is the reflected wave B3. So these incident and reflected waves, as we know, are related to each other by a scattering matrix, S matrix, as the reflected waves B1, B2, B3. The reflected waves are related to the incident waves A1, A2 and A3 by a set of parameters called as scattering parameters, which we have obtained as 1 by 2, S11 is 1 by 2, this is S12 is minus 1 by 2, this is 1 by root 2, minus 1 by 2, 1 by 2, 1 by root 2, as can be seen from this matrix above. Then 1 by root 2, 1 by root 2 and a 0. In equation form we can write as B1 is 1 by 2A1 minus 1 by 2A2 plus 1 by root 2A3. B2 is equal to minus 1 by 2A1 minus 1 by 2A2 plus 1 by root 2A3. And B3 can be written as 1 by root 2A1, 1 by root 2A1 plus 1 by root 2A2 plus 0. So there is no need to write anything. So let's name it as equation, say for example 5, 6 and 7. Now let's discuss two special cases. Case 1 would be that we are applying or we are connecting a source here. That means A3 is non-zero. We are connecting a source at port 3 and we are not connecting any sources at ports 1 and 2. Rather, we can connect at ports 1 and 2, we connect some loads. So A3 is not equal to 0 as we are connecting a source here. A1 is 0 and likewise A2 is 0. So this is our case 1. When we are connecting a source, we connect a source at port 3 here, at this port 3, and we are connecting loads at ports 1 and 2, assuming that the loads are matched to the port impedances. Or in other words, we are connecting, in simple words, we connect a source at port 3 and we are not connecting anything at ports 1 and 2. So that means A1 is 0. A1, so far is concerned, A1 has to be 0. A2 has to be 0 and A3 is not equal to 0. This is our case number 1. So case number 1 is A3 not equal to 0 as we are connecting a source there. A1 is 0 and A2 is 0. So if we look at these equations, B1 in this case would be A1 is 0, A2 is 0. So B1 simply would be A3 upon root 2. And likewise B2, equation number 6, B2 would simply be, this would be 0, this again would be 0, it would be simply A3 upon root 2. And so far as B3 is concerned, equation number 7, B3 would be 1/2 of 1 over root 2 A1, 1 over root 2 A2, A1 is 0, A2 is 0, so B3 is simply 0. दरवाजा बंद मुझे भी काम है जिगर 5 मिनट के बाद आना. Can be written as 10 log now let ओके कोई बात नहीं. So what we have seen is that the power at port 3, B3, is simply the addition of the two signals coming from ports 1 and 2. So in a nutshell, what we have seen from these, what we have concluded from these two special cases is that if I have an H plane T junction with 3 ports, port 1, 2 and 3, when I feed a signal at port 3 or when I am giving some power at port 3, it gets equally divided between ports 1 and 2. So in this case it acts as a 3 dB splitter. But in the other case when I have this when I have this H plane T, now if I connect a source here at port 1 and another source at port 2, the two signals, they simply combine and the sum of these two signals comes out from port 3, as can be seen from this equation. So in both these cases, what we have seen is that an H plane T junction, either it has acted like a combiner of power or a splitter of power. So that's all for the day. Good day.